Okay, so let's get started. Let's get started. Hi everyone, I'm Wim Oudenaert. I'm CEO and co-founder at AM Team. We will go a bit deeper in who we are and who is all in this webinar, who are the hosts, who are the panelists. But yeah, it's my pleasure welcoming you on behalf of our whole team. It's our third Amazon webinar. We actually have over 100 subscriptions. It's very nice to see that people, well, the former attendees of other webinars or the past versions, let's say, were very enthusiastic. They keep coming back. So for all of you that have attended previous webinars, a big thank you. And for all the new people, well, we have selected some very good content again with some new learnings. And also for the people that have attended, again, some new content will be presented. So we will be talking about, let's say, what we call Ozonation 2.0, the next generation ozone process, optimization, design, and monitoring. And today we will zoom in on specific topics, including bromate formation, and also how you can smartly design and operate your plants. By the help of AMOZONE, which is the simulation model we have been working on for over 4 years, actually. So let's dig into the content because there's, again, as usual, a lot of stuff to talk about. What are the objectives of today? Well, let's first put things in a context a bit. So our company AM Team is currently deploying the Amazon simulation model services at the international scale. This means, to make it very short, we are using this model to help designers, operators worldwide to suppress bromate, to save costs, and to better design plans. What are the objectives of today is that you will go, we really hope that you will go home, or let's say you're already home. I mean, you will close the webinar with some new detailed process insights that can have serious practical value for you. And also that you get a bit more familiar again with the principle of process simulation and how it can actually help practitioners to solve practical problems. The format of this webinar is similar as last couple of webinars. It is a hybrid, so it's a mixture of live slides, presentation, but also demos. So we will go to colleagues from time to time that will show real time simulations, and then we have also the Q&A. So we invite you to ask a lot of questions because we have colleagues continuously monitoring the Q&A. So questions and answers can be posed in the Q&A window. So if you go over your screen, you see the Q&A button. Don't use the chat, use the Q&A window for the questions. And then we will come back to them. And actually the most interesting ones or very relevant ones, we will answer live. After the webinar, there will be a short questionnaire. If you actually forget to fill it in, we will send you an email anyway, because we value feedback a lot and we will really want to keep improving these webinars. But also we are interested in the next topics we should be tackling or we should be highlighting with the next webinars. We will start with a very short introduction. It's only 2 slides. Then you know who is talking, who are we. But then we will go into the content. And there's a lot to talk about. We will be talking about dosing strategies of ozone and also the impact of dosing strategies on bromate formation, because bromate is always an important topic in ozonation systems. And also we will be zooming in on the impact of water matrix and long-term dynamics, because even if it's a drinking water plant or even if you have an industrial site, you would assume it's more stable water compared to, for example, secondary effluent. Well, they all have dynamics, and the dynamics are important. And then we will shortly touch upon the implications of the costs. Let's start with ourselves. So we are AM Team. The name of our company was actually derived from the A Team, which is a special force. Some of you might be familiar with the A Team. But AM stands for Advanced Modeling. So we provide cutting-edge process simulation services to the global water industry. I'm pretty sure you are familiar with many of the logos on the slides. Our customers, we have a lot more, but not all the logos can be shown. But they are three big categories. There are people designing installations, there are people scaling up or developing new processes, and then we have the end users operating processes. And we help them with very realistic process simulation, both at CFD, so computational fluid dynamics for very good reactor designs. Now we have dedicated kinetic models to actually save energy, improve performance, and things like that. We work at the global scale. As you can see on the world map, we have our customers or projects everywhere. Our company is headquartered in Belgium. This is the team, the current team, but actually it's not the current team. This picture gets outdated all the time because we are hiring quite some people. But who is present here? Well, I'm Wim Oudenaert. I'm CEO and co-founder at the M team. My background is actually ozonation, advanced oxidation. I did a PhD on that topic. So it's very, very close to my heart, but it's also very close to the heart of my colleagues. For example, we have Roberta Muyo. Roberta is actually an advanced simulation engineer. There she is. And she has been working on AMOZONE quite a bit, and she will be showing demos and simulations. And now we have also in Italy, so Roberta is in Italy. Giacomo is also in Italy. We have Giacomo Bellandi. He's senior simulation expert at the M team. And he has also been involved very seriously in the ozone modeling. Has a very in-depth background on data processing, modeling, process modeling. And then we have Celia de Wilde. Celia is actually business development manager in our company. Celia, well, she works with a lot of key customers in the water industry, and she will be helping us with the Q&A. She will be helping to structurize all the questions and bring them live in front of the audience. And together with her, Willem will be doing that actually. Willem van Doorn is our marketing communications manager. Hi, Willem, there he is. And he's also joining this webinar to make sure it all runs smoothly. So this is the team, right? This is the team for today. For people that that really are addicted to this content, there are some. I don't think there are a lot, but there are some people addicted to this content. They can always visit our website, amteam.com/Amazone. And actually, you can even go to our YouTube channel where we have a dedicated playlist on Amazone with all like little movies and a lot of in-depth material. But let's start on the content, okay? Let's start with the first important topic. How is bromate actually being formed? And the question that is important for practitioners is, can we do something about it? So let's look into bromate formation. If you look into bromate formation, I'm pretty sure all of you, if you're a bit familiar with how ozone works, you cannot have bromate without bromide, Br minus. The higher your bromide in your water, the more bromate you will have. That's like the rule of thumb. But it's not as simple as that. Huh? So how does it happen? In one way or the other, you have to go from bromide to bromate. It's not so obvious because there is a lot of chemistry involved. Yeah, don't get confused by this very complex chemistry scheme here. A lot of people in the past have been working on this. But just remember two things. The first one is bromide can either react with hydroxyl radicals. The second one is bromide can also react with ozone. So it's either one of those that makes you will finally end up with bromate. But just pay attention to this route. Okay, just imagine it reacts with hydroxyl radicals. Okay, it forms some intermediates, but you still need ozone along the way. You still need ozone here for the final step as well. So the conclusion here is to have bromate formation occurring, you actually need dissolved ozone residual. So having ozone is even not enough. You need some local dissolved ozone residual. This is also the reason why advanced oxidation processes solely relying on hydroxyl radicals, one example is UV peroxide, don't have bromate formation because you have no ozone to do the final work. So this is important to remember. Two steps in the beginning, and then different things happen. It's very complex in real water. But what are the practical implications of that? What are the practical implications? We will now do a small demonstration for you. We will gradually build up this story. So we take everybody and everybody understands. So we will start very simple. We will start at the batch scale. So just imagine you are in the lab, you have some of your water sample, whatever water sample you have, and you pour in some ozone. You pour in an ozone stock solution that has pre-dissolved ozone. So it means you have no gas phase. You have a different system or different beaker where you bubble through ozone, ozone dissolves, and this is your ozone stock solution. It's all dissolved. For example, 60 milligrams per liter. It's very reasonable. You add a part of that to your beaker, and ozone starts reacting. That's a very small, simple experiment. I think everybody understands. Now, this is an important thing. What would there be a difference if you add all of your ozone all at once? Just imagine you add 5 milligrams per liter all at once, or you add it in 3 times. So you divide the volume in 3 parts, and you add a first volume. You wait like for 20 seconds. You add a second one. You wait for 20 seconds, and you add the third one. In the end, you have actually applied exactly the same ozone dose. So here's a small question for you. So let's do a small poll. Here is a poll. Normally, there should be a poll on the screen. Here's the question. Imagine you add everything at once, and you have a formation of 13 micrograms per liter. And imagine you do exactly the same experiment, but you add it in 3 times. What is the residual bromate you will be forming? And you can vote actually now. Is it 8 micrograms per liter, 10, 13, or 15? So let's see what the audience thinks. Okay, there is quite some things happening here. It's a live poll. More than half of the people have voted. Yeah, it's very close. So I'll end the polling within like 3 seconds. Give it your final thoughts. I hope the results will appear here on the screen. Yeah, I hope you can see them. But anyway, the winner is 8 micrograms per liter. It's like 47% of you that really believes you will have much less bromate. And then it's like divided. But quite some people, like 25%, 1/4 of the audience also thinks you will have higher bromate. So 15 micrograms per liter. So I will share the results. Normally, you can see the results right now on the screen. So 8 is the winner, but there are quite some people also thinking that you will have higher bromate formation. Okay, well, the best way to illustrate this is to go live to our colleague Giacomo in Italy. Giacomo, you can take over here, and you can give the final answer and the demonstration.
Yes, let me share my screen. What you see now is the Sumo platform, the platform that we use to implement to embed the AMOZONE model. What you see here is the representation of the example that Wim just mentioned. A single beaker with some water inside with a certain characteristics in terms of organic matter, of inorganic components, and other constituents, and certain pH, and so on. So a certain water matrix in a beaker in which we are going to dose a single shot of ozone, 21 milligrams per liter of ozone all at once. Now, what you see here is what actually happened in a batch experiment, and you see the measured data points here and the model fitting through it. Now, for the ozone residuals, and in red, you see the bromate formed. So it starts at 0, and then it builds up little by little, very suddenly, and it ends up to an end concentration of 13 micrograms per liter. So if we run this, then you can also see it run live. It is a very high resolution simulation. It's 0.1 seconds of data interval for a bit more than 5 minutes. And then you can see the ozone profiles dropping very fast in the initial stage. Why? Because the ozone dose reacts very fast with the organics and the water matrix. And then when the fast reacting part is finished, then it starts reacting with the harder part to be degraded of the organics, and also with the inorganic matrix, and then it starts decaying in time. At the same time, you have the production of radicals and ozone. At the same time, in high concentration presence, this will give the first very rapid jump in bromate, and then it increases also quite fast in the second part, where the radicals concentration, which we can check here. So the radicals are what you can see here. It's that in a matter of milliseconds they are disappearing, but they are depleted very fast because they are fast reacting. And here what happens is the bromate formation of the lower part of the reaction scheme that Wim showed before takes more importance, and until we reach an end concentration. Now, what happens if we divide then this dose in 3 doses is that we start with the original water that we took at the beginning. So no ozone is added at this time. And we are going to give a first shot of 7 milligrams per liter of ozone. Now, what happens is that if we take out the original measurements for the single dose, then we see that the 7 milligrams of ozone per liter, they are very fast depleted because it's a small concentration, and the fast reacting part of the organics and the water matrix reacts very fast with the ozone, and it depletes the ozone in terms of few seconds. And then 0.8 micrograms of bromate are formed. But now what happens if we give a second shot is that the initial depletion of ozone is slightly lower because there is less of the fast reacting components in the water matrix. And then the lifetime of ozone, it's a bit longer, and there might be more bromate formation in the second part of the reaction, which leads to 2.4 in total of bromate form. Then if we, on top of this, reach a total dose of 21 with the third dose of 7 milligrams per liter, then we can see the bromate increasing, and who's the winner is those ones that actually the majority, or if I remember well, almost the majority voted for 8 micrograms per liter. So congrats. That's what happens. That splitting the dose in 3 small doses, so having the overall dose the same as the single dose, helps in controlling bromate formation. Why this is happening? For a complex net of reasons, which is the link to the complex net of reactions that lead to bromate formation. In a nutshell, you leave more chances to the reactions that take away the BR formed in the middle of the way of going to bromate, to the final bromate formation, to be dragged back. You also improve a little bit more the scavenging of the radicals. On the other hand, you might lose some, but a very negligible part of the potential for micropollutants residual. Here, what you see is the removal of some of the micropollutants that we have here. It's just some examples. They are depleted in a comparable extent to the single dose. So the message is the micropollutants removal do not change significantly, but the bromate formation, it can be controlled in a very important way. And then we can go back to Wim's presentation for the second part.
Perfect. Thanks, Giacomo, for this demonstration. So yeah, the correct answer was indeed 8 micrograms per liter. It really looks like a very simple, very obvious for many people, very simple, but it of course has a huge practical implication if you look at system design, and this is very important. So let's go to the dosing. How ozone is dosed in systems nowadays? Well, there are like let's say two very accepted ways. The first one is the side stream injection. So you have a certain side stream. Part of your water you take out, you ozonate it, you inject a lot of ozone in it, and then you reintroduce the side stream in the mainstream. This is like a pipeline reactor, but you have different kinds of systems. That's one way, of course, many of you are familiar with it. The other way is bubble diffusion, FBD, fine bubble diffusion, are also a very well-known way. Huh? Well, of course, they are very different. And uh, we will now actually build up the story a bit more, and let's now do a similar run, but we will now be looking at a real plant. So for this, we will go to our colleague Roberta Muyo, and she will be sharing her screen and do another demonstration for us.
Yes, thanks, Wim. So good afternoon to all the participants. In this lab demo, we'll be looking at a virtual full-scale plant. So it is the layout is here. You can see it is a sequence of bubble columns, both current and counter current. So you have the influence here, then the flow enters the first bubble column, which is made by a small compartment. So the first compartment is called BC11 and is here at the top. Then the flow goes down to the second compartment and then to the third compartment, which is called BC13, in which the ozone is dosed via the diffusers. Then the flow goes to the second bubble column and so on till the effluent. So in this exercise, we will first dose a certain amount of ozone, a certain amount of gas flow in a single bubble column, in BC1. So for instance, we are dosing 1000 liters per minute in BC1. Let's see what is the effect in terms of ozone residual and in terms of bromate formation. So the simulation is finished and we can now take a look first at the ozone residual there. So here in this bar chart, you can see the concentration of each variable in each compartment. So here now we are looking at the ozone concentration from the influent then to the first compartment of the first bubble column, second compartment, third compartment, and then the flow goes on to the other bubble. Is that the ozone concentration, the ozone residual, is higher in the third compartment of the first bubble column, where we are dosing ozone. Then there is some ozone residual downstream and also some ozone residual upstream in upper compartment of the BC1. Now, if we look at the bromate concentration, we see that there is a spike of bromate formation where the ozone residual are highest. And also there is a little bromate formation downstream and a little formation of bromate upstream. But downstream in our installation, there is no ozone residual, so no more bromate formation will occur. And in the effluent, we have, in this case, 16.8 micrograms per liter. Now let's see what happens if we split the dose in two bubble columns. So now we are dosing the same amount of ozone, the same amount of gas flow in BC1 and in BC3. Now let's see what happens in terms of ozone residual and especially in terms of bromate formation. Now the simulation takes a few times to update. in the meantime, we can also see that we can check a lot of plant-wide variables, so we can monitor and time dynamically the ozone transfer in each single bubble columns, the ratio, the ozone ratio respect to the DOC, the overall dose, and so on. And now we can go back to the bar chart. The results are uploaded. Now we see that the highest ozone residual occurs in the third bubble column. So in here, close to the diffuser, there is some ozone downstream in the next bubble column and some ozone upstream. There is also some ozone in BC1. So what we did now, splitting the dose in two bubble columns, is letting the ozone react first with the organic matrix, with the organic compounds, the water metric in the first bubble column, and in this way we allow ozone to increase ozone lifetime downstream. And in terms of bromate formation, in this way we are controlling the bromate formation in the first bubble column, and then the spike of bromate occurs in the third bubble column. Then we have again a little bromate formation in downstream, and since there is no ozone residual downstream in the other bubble columns, the effluent concentration stay constant, and now it is equal to 14 micrograms per liter. Now let's do another try and split the dose across 3 bubble columns. So again, we are dosing the same amount of ozone, but in this time we are dosing in the first bubble column, 33% of the dose in the first one, 33 in BC3, and 33 in BC5. So let's see what will be the effect on bromate formation. Okay, we are almost okay, we are there. Now we can see that the highest ozone residual occurs in BC5, again close to the diffuser. There is some ozone residual in BC3 and in BC1, but let's see what happens to the bromate. So the bromate formation in BC1 is now very limited, it's only 0.6 microgram per liter. Then we have a small jump up in BC3 to 3 micrograms per liter, and the highest formation occurs in BC5, in the last column where we are dosing. But in the effluent, now we have almost 12 micrograms per liter. So summarizing a bit, in the first simulation, we dosed everything in the first bubble column and we got 16.8 micrograms per liter. In the second simulation, we dosed 50% of the gas fluoride in the first one and 50% in the third one. And we got a concentration of bromate equal to 14.3. And now we split the dose across 3 bubble columns and we got an effluent bromate of 12. So just changing how we introduce bromate in our system, in our installation, can help to lower the bromate formation to 30%. So thanks, Wim. We can go back to the slide.
Perfect. Thanks, Roberta. Yeah, I also want to congratulate my colleagues for the braveness doing live simulations. We could have recorded everything here. And as people working with live demos know, yeah, it's always a challenge. You have to do it in front of a live audience. So thanks for having the guts for that. So let's go to the conclusions of this section. There are 4 take homes here. The first one is the removal of target contaminants is actually much less, it should be much less, there is a typo here, much less affected by your ozone introduction strategy compared to your bromate formation. So you can have similar removals of your target contaminants with splitting doses, but you can have very different bromate formations. There can be some differences in the target contaminants as well, but we are talking about like 1-2% or so. So it's very subtle, very small differences. Actually, you can design plants for minimal bromate formation by spreading the dose. But of course, I have to go to the third point. I think our team actually thinks working with all these different plants, drinking water, wastewater, some are industrial water. It really depends on the matrix a bit, how your ideal plant would look like. And there can be some subtle differences that can have huge impact because it all depends on your matrix and how your local ozone, so not the overall ozone, but your local ozone builds up in the system. We believe, for example, if you look at two extremes, drinking water ozonation systems where you need a residual, you need a CT, and when you look at, for example, systems for micropollutant removal in effluent, probably these systems should look very, very differently, or they can at least look very differently because the concept is completely different. In fact, there is also a lot to do as we as practitioners know about side stream versus bubble column. Yes, there are differences in costs, in maintenance, pros and cons for each, but there are differences potentially in bromate formation as well. I'm not saying that side stream is inherently leading to higher bromate formation. There are side stream systems out there that produce very limited bromate. But in fact, if you talk about keep the HRT in the side stream short, because that's the general guidance, if that is too long, your bromate goes up very, very fast. Well, actually, you are saying do not allow all ozone to dissolve in the side stream. Because if that would happen, you go very, very similar to this first column Roberta showed, which is the more drastic case of a very, very fast transfer of your ozone in the water. So it has to do with the amount of uptake of your water locally, and also the amount of local transfer efficiency you have. This will, in the end, determine your final ozone residual, and your final ozone residual then leads to your local bromate. So if there are any questions on this topic, I would invite everybody to ask questions in the Q&A. We can come back to them if there are questions. So in the meantime, let's go to the second topic of interest here. So the importance of the water matrix and the practical implications of that. Actually, water matrix, or deciding if ozonation is a suitable technology for your site or for your matrix, it's much more than looking at bromide levels or DOC levels. There are some general guidances. For example, if you look at wastewater effluent and it has bromide higher than 150 or 100 micrograms per liter, you could say, well, there is some risk for bromate. If you're lower, you're safe. But we have seen plants where you have much higher levels and still limited bromate formation. So it really depends on not only on the DOC, it not only depends on your bromide, it depends on a lot of things. What are the other things? Examples are nitrites, ammonia, carbonates, temperature, pH. There are lots of things to say about this. We can have actually 5 webinars on each of those separately because there is simply a lot of chemistry involved. One example, this is actually a table from a recent paper co-authored by us and a couple of other folks from the US and also France. I think Heather, who is the first author here, this was a WebTech paper. She's also attending this webinar. But there's one table there. It is not a complete table, but it summarizes, okay, per variable, what is the impact on your system? Because some variables affect your ozone and hydroxyl radical levels, but other variables also affect the bromate formation mechanism as such. pH, for example, has an impact on all of them, including bromate suppression strategies. Even if you dose peroxide to suppress bromate, pH has an impact. So it means if pH changes, all of these 3 things change simultaneously. And this is causing a lot of non-linear behavior, looking across plants, looking throughout time. But you can see that there are other variables of interest. Another example is alkalinity, which scavenges your radicals, right? Ammonia, for example, has a very, very big impact on bromate formation because it will scavenge part of your bromide to form monobromamine, actually. So this is, these are all things you have to understand. You don't have to know them by heart. They're all included in the model, but there is a lot of things going on. But to make it practical again, we will go back to Italy to our colleague and show a demo on this impact of the water matrix. So Giacomo, the floor is yours.
Yes, thank you. All right, let's go once more to the Sumo platform to have a look at what is the impact of a dynamic influence on your effluent chart. I mean, on your effluent bromate and your micropollutants conversion, for instance. So here you see the layout that Roberta just showed, and then here is a time a data set of the influent with the flow rate, with the UVA as an indication of the organics, dissolved organic carbon, ammonia, and nitrate. Then you also have the model gets also nitrite, alkalinity, and many other variables as an input. If they are not available in your case, don't worry, we deal with it. There is no problem. We can live with less variables. But what I want to show you here is the effect of highly fluctuant dynamics on the final effluent. What you see here is the flow rate with some rain events over 20 days. Let me continue the simulation because I stopped it for 1 second, then you can see it progressing. And then you have here the UVA absorbance of this influent that is coming into our installation, and the organic, dissolved organic carbon, ammonia fluctuation, and so on. So every one of these variables will have an impact on your final bromate formation and also on the micropollutants removal. So, and as details are important, then all of these variables will affect both the ozone lifetime, so the ozone residual in your in the installation, and will also then ultimately also affect the lifetime of radicals, because changing the water strength with the rain events, you can get dilution. Your radicals might live longer, your ozone might live longer, and you might end up with very high peaks of bromate form, like in this case, up to this is up to 25 micrograms per liter. And why this is occurring? This is different reasons counter-occurring at the same time, occurring at the same time. So what you see here as the residuals of ozone at the end of the installation, it means that at this point in time, there was a rain event or some dilution caused by different factors, which made the ozone dose in the system be excessive, because here we are just blowing without control a certain amount of gas in the 3 columns. We are splitting the dose, but we are not efficiently controlling the dose. So in this case, the dose of ozone might be excessive, and you get residuals. This low residuals, apparently not even measurable in an effluent, will affect the bromate formation and the whole installation. So this has an important effect in design. And what happens in the deeps? In the deeps, sometimes the presence of ammonia helps knocking down the bromate form, as Wim anticipated, but sometimes the sole ammonia presence is not enough, because the matrix composition does not make the life of ozone and radicals short enough, and then having residuals for a sufficiently long time in your installation makes the bromate forming. At the same time, what happens is it's very high. what you see here is very tremendous dynamics in your performance of micropollutants removal. You have here a 10 minutes frequency data set, so you have very, very high resolution data plotted here over a time of 20 days in the simulation. And then you can check the plant-wide variables to check how much is varying the ozone dose in your installation throughout time. But what you can notice here is how much the influent variability, the influent composition, the water metrics changes, even though it's the same water source, the water matrix changes in a way affecting very much the ozone residual and the effectiveness of the ozone treatment. All right, then we can go back to the presentation.
Thanks, Giacomo, for the nice illustration of the full-scale plant dynamics. So Giacomo has actually shown this dynamics. So not a single plant is actually static because everything is varying. Even drinking water has seasonal variations. So if you look at wastewater effluent, it has more diurnal and weekly variations. Or of course, precipitation, rain is very important. In drinking water, the seasonal variations are very important. For example, ammonia and nitrification things in surface waters are very impacting. So typically you have all these dynamics, and the most important ones are, of course, flow rate, dissolved carbon, and we all know if you have a certain installation designed and your flow rate decreases, but you still have the same ozone system in place, your bromate might also be affected, go higher if you push lower flow rates or increase the HRT, the residence time in your plant. So, well, what we typically see in both drinking water, but also especially in wastewater effluent, is the high impact of ammonia. So if your upstream ammonia fluctuates, your bromate will fluctuate with it. Typically, this is not visible in practice because typically you take very few samples. Either it's a grab sample or, for example, a 24-hour composite sample, but there is no online sensor for bromate. So unless you really take grab samples every 10 minutes, you cannot really capture these peaks. But in the end, in any plant, you have the average bromate, which might be reasonable, but there are definitely bromate peaks. There is no doubt about that. They are caused by pH fluctuations, but ammonia is a very important one. We have seen in some plants an almost one-on-one relationship. So this brings us to the conclusions of this webinar. But before we go there, I will go to my colleague Celia and ask if there are any questions.
Yes, thank you, Wim. Yeah, one question just popped up. Yeah, if our software or the model is capable of running a control loop to take different quality parameters as input, for example, DOC level or other parameters.
Yeah, well, that's something I will talk a bit further on this slide. But that's a very relevant question. And yes, this is a project where we are establishing currently several projects where we will use the model as a digital twin. You have heard the word digital twin a lot, I'm pretty sure, but not many people know what it exactly means. And even less people know what the practical value is. So I will try to illustrate it a bit here. But in fact, it comes down to, okay, let's feed this model with very simple sensor data, pH, UV254, flow rate, which is also a sensor, right? Let's run these basic variables through the model and then ask the question, can the model give us back things we cannot measure? So you predict variables you are interested in but cannot measure based on variables you can measure. Very good examples are the target contaminants, bromate, or CT, including dissolution CT in columns and and even side stream systems. Okay. So are there additional questions, Celia?
Yes,
Okay.
some came in. I'll start with the one from Ula. If we can create a digital twin for a completely new dissolution device.
That is definitely possible. If it's a completely new dissolution device, we have to probably take a look at it. And there are two avenues to take there. Either you start with a CFD simulation, because we have the direct coupling of this kinetic model with CFD, so computational fluid dynamics, these 3D flow simulations. This will definitely give you a very, very good idea on the local transfer and local bromate formation of this device. But on the other hand, if we can conceptually model it with the model my colleagues Roberta and Giacomo have been showing, that's also possible, because then you have a digital twin and you can feed it dynamically. It's definitely possible to design equipment and to design reactors or other systems, yeah, with the model.
And then maybe another question is about the input we need, which data we put in, because yeah, what kinetics are needed, and if we can take into account several seasons, long periods, and if we have developed the means to estimate demand and decay on typically available information, like TOC, UVA, temperature. So maybe you can elaborate a bit on how it practically works for using the model.
Yeah, perfect. Yeah, so when we started developing this model 4 years ago, the basic question we asked ourselves was, well, okay, let's develop this model, but under the condition that the model can be fed with basic data. So you can build a very sophisticated model, but if it needs very complex inputs, it's not really practical. So this means, indeed, if we go to the question, we typically feed the model with data that is very readily available at plants. A very important one is flow rates. Another one is some samples on DOC, or some people have the online DOC, or some samples on UV254 absorbance, or some people have some spectral online data. Many people have ammonia profiles, nitrites. So we start working with that, and we can already get a long way with that. Many things are correlated to seasons and flow rates, so we can also fill up a lot of gaps. And typically, what we do is we build the model, even if there is no ozone installation on site, we build the model, we feed it with the existing data of the existing plant, and the outcome is actually basically the future performance of a future installation if you would put it there. We calibrate the model specifically for the matrix. So every matrix is different. Not that there are tremendous differences, but there are subtle differences that are very important. Next to DOC levels, we are also talking about organic reactivity. And then we do a basic calibration based on dedicated batch experiments, very simple batch experiments, typically 3 to 4 samples collected in a period of a month or a few weeks. And we calibrate the model based on that, and we can also get going with that. If the plant, of course, is existing and there is existing data from ozone sensors, or there is existing bromate information, we can also work with that. So these are typically the ways how we make it work at plants. Okay. So I will just finish this slide, and then we can come back to the residual questions, Celia. Okay.
Okay, perfect.
So this brings actually everything together, because I can understand that it can be overwhelming. Okay, wow, where can you now use this, and how can you now really practically apply this? We have seen 4 big phases. The first one is the selection of a treatment technology. For example, you are deciding on, should we put ozone here, or would activated carbon be a more suitable technology? You are in the phase of deciding which technology to put there on site. So the questions you have is, is ozone suitable? If so, what is the bromate potential? What is the cost and performance of this future full-scale installation? Typically, people put pilots on site. They run it for a couple of months to over years, and then they collect a lot of data to see what the performance is. We have actually been replacing complete pilot trials with this model by, again, feeding it with the real sensor data or the plant data. And this is what we call virtual piloting. So we do the virtual piloting on site, which gives you a very good idea on including these dynamics you will face in if you would put a future full scale on site. Of course, then if you have decided, okay, let's put ozone on site, you have to design it. Typically, design has two big stages. The first one is the conceptual design, basic sizing, basic ozone demands, basic estimations of costs. This is conceptual design. Typically, we use a very similar approach there. We built this full-scale plants or several full-scale candidate plants with different volumes. We test different ozone control strategies. Should we go for a delta UV, DUC proportional, flow proportional, maybe a hybrid of those? And you can run them through the model to have the conceptual design. So questions there are the size and of course, the performance of the installation and the cost. The second step of design is the detailed design before you build. These questions are quite different. You have been deciding on the capacity, you have been deciding on the size, but you still have to make some decisions on, okay, where exactly do we have to put the diffusers? Where exactly should we put the baffles? Should there be baffles in the first place? What is the shape of the reactor? Things like that. You can clearly answer them with CFD. So the questions we have there are related to transfer. What is your transfer? Can we optimize, maximize the transfer, baffle placement, mixing? And of course, your local hydrodynamics have a drastic impact on your local residuals. And I shouldn't explain it, right? It also has an impact on your local bromate formation and your overall bromate formation. So don't underestimate the importance of this second stage, because there are really a lot of wins to be made there still. And of course, once you have built it, you can use exactly the same model to run it virtually as a digital twin. So this means you have a computer next to your plant. Actually, it is fed with the same sensors of your plant, but the model predicts and gives you in real time your bromates, your CT, your cost, or your the removal of whatever amount of micropollutants. So this is the digital twin application. And you can see that they nicely connect. Once you have a model in the first stage, you can actually use it throughout the whole cycle. So this was just to bring it together to structure your mind a bit, to help you seeing this this whole forest of applications. But in the end, it's quite powerful. Huh? It's really digital twin application. So before we go to the next questions, because there is still, if you have questions left, we will continue still a bit, but we will launch a final poll here on, let me see if I can, yes, I can launch the poll. What would be a very interesting topic for you for a next webinar, Amazon webinar? It's not that we will only limit ourselves to that, but we would be very interested in that. So for example, the online digital twin application I just talked about, or the impact of diurnal or seasonal water quality changes on ozonation, different bromate suppression strategies, for example, peroxide, monochloramine, or really other strategies you can, like adding chemicals, or cost savings from virtual piloting, or cost savings from operation, like having smart controls. So what would be what would be carrying your interest here? We would be very interested in hearing about that. So the results are coming in. It's quite nice to see. All right. Yeah. Most of you have voted. Let's give it like 1 more second, or well, 3 more seconds. Okay. So I will share the results with you. Most of the interested, well, clearly that was actually the prediction of Giacomo, that many people are concerned about costs and want to see how cost savings can be done. So that's a very good topic to focus on next time. And we will also try to include a couple of the other topics. But cost savings can be both OPEX and CAPEX. CAPEX can really be also optimized, we think. Okay, so this brings us to the final slides. Before we end with the final Q&A, because we still will answer a couple of questions. Well, the end conclusion of this webinar is, well, we expect really to keep removing significant practical, regulatory, and financial barriers with regard to the application of ozonation. One example is, what if you can replace a year of piloting with 6 weeks of simulation? And this was a real case we have actually recently finished in the Netherlands. So there are really many gains to be made. Also the digital twin application. And we want to acknowledge a lot of partners or people we have been working with. I will not go over all of them, but it's a mixture of knowledge institutes, companies, utilities that have been joining us in this adventure. And also our simulation team, of course, the AMOZONE simulation team, Giacomo, Roberta, and Miguel. Thanks a lot for your commitments. Good. So Celia, I will go back to you. Before, if you would decide to leave now, please don't forget to fill in the questionnaire. Okay, that will pop up. And if you still want to stay with us for a couple of more questions, be my guest.
Okay, Wim, I'll jump in. There were a few remaining questions about the presence of metals in the matrix. How is it taken into account in the model and how? And then also with regard to NDMA in our model, if that's one of the contaminants that's in the model. Maybe Giacomo or Wim, I don't know who wants to answer that.
Yeah, yeah, sure. What I can say, so metals is not really something that we've been focusing on, but it's surely processes that can be included. And when I say can be included, if we define today a set of interesting reactions that would suit your interest and serve it at the purpose, tomorrow can be included in the model. So it's as well as additional micropollutants or side products of the degradation, whatever is interesting for the specific application, the power of the model. It's also the ease with which we can adapt it to certain different applications.
Yeah, exactly. So we are talking about a mechanistic model. So this means the model is really based on chemical reactions. It's real chemistry. And we build it up gradually, modular. For example, initially, the first version of our model didn't have bromate in it. We added the bromate module only later. So that's where we are continuously working on model extensions. But we hear it more and more. More and more people are looking into the byproducts. NDMA, well, NDMA can be a potential byproduct. Yeah, in the future we can definitely work on that to include it. For now, we focused on the most urgent thing and pressing things that were bromate and the target contaminants, the parent components.
Yeah, and then another very interesting question came in, how we predict the acceptance of the model in the broad market of modeling versus on-site pilot testing. Then we look a bit more higher level, but I think it's an interesting topic also, maybe even for a next discussion.
Wow, I don't know who posed that question, but it's a it's a powerful one. Yeah, it's a very good one. I mean, exactly, it's a very relevant one. We are working in the water industry. The water industry has some regulation around us, right? We have some regulation. There are some other regulated industries. Plus, if you design something, it should be there for 20 years, 25 years. Plus, the infrastructure investments are huge. There are a lot of things. I mean, what I appreciated very much lately was the PhD of Paul O'Callaghan, which is a PhD at Wageningen University on innovations in the water industry. And there you can see that it takes time. It takes time to enter with something new. The benefit we have here is it's a digital solution. So we are not offering a new technology that needs a lot of time and effort to be built. So we can expect it to go faster, but still it's a mindset shift. It's a culture. If you are used to doing it that way, you have to have good arguments to get it replaced. And the only thing I completely understand people that are very skeptic to this. But I think we are working together with a lot of industry players. And if you have very good collaborations, you can criticize this way of working very much, try to destroy it. But in the end, if it really gives extremely good results and cost savings, I think it's a matter of time. Here it will really, get mainstream application. So we are doing our best. I think the only thing we can do is keep demonstrating the value of it and keep coming back to the cases we have and update the results on that and communicate on these latest findings. Yeah. So definitely a lot of things to do. Yeah, but especially the virtual piloting one, it's a really strong business case. Huh? I mean, 6 weeks or 1 year of piloting, it's a very strong business case.
We recently had some experience and with virtual piloting, where we have seen the practical value of it. I mean, also seeing the changes in the legislation that occurs very quickly and are about to enter in legislation the real limits, then it's a matter of a few years and might not be very feasible with actual pilot, so real life piloting, also in terms of expenses, personal and materials.
I think a nice addition to this is that we are now working on a couple of projects where people have built physical pilots or physical demonstration installations. They are really up and running, or they are under construction, so they will be up and running. And our model will run with them in parallel. And that will serve, of course, as excellent cases on really advancing the learnings even further and demonstrating the value further. So these cases we will definitely come back to in the coming months as soon as we have more results. Other questions, Celia?
No, I think that was it for now.
Okay.
Anyway, I think if people have additional questions, they can always contact us. We are happy to help. So
correct.
I think we can end the webinar. One of the questions, a practical question about recording. We record all our webinars and we share it. So once the recording is processed, we will share the link with all of you.
Correct. Yeah, exactly. Okay, so then with this, of course, take a look at our website, YouTube channel. There is really a massive amount of information on that. Send us an email, info@amteam.com. And for the rest, I think, help us with improving by filling in the survey. And then as a final word, I will say a big thank you. A big thank you for everyone for attending, because attending a 1 hour webinar is always heavy. And we are all saturated by webinars nowadays. So thanks a lot.